So welcome students. In today class we will study about the reverse osmosis. So we have already studied this topic before the mid semester, and today I am only the repeating the main part of these topics. So we will start with the applications of reverse osmosis. So reverse osmosis is the most useful process or widely useful process among all the different membrane based processes, separation processes. So basically reverse osmosis is primarily used for the water purification and for producing the portable water or the drinking water. It is used by the municipalities, where it is used by the restaurants, hotels. We use the reverse osmosis in the homes also, and it is also used in the offshore oil rigs. So this is the actually reverse osmosis used for municipal waters, also for river waters or groundwater, for purifying the groundwater, river water also, and also for the sea water also. So it will produce the portable drinking water from the groundwater, from the river water, or from the sea water in the different applications. Second is the for production of the ultra pure water. So in the different industries we need the ultra pure water for the reactions as well as for the different other operations, like in the boilers or drug formation and other things. So for that also we can use the reverse osmosis process for production of ultra pure water, where the salt concentration of the concentration in the water will be very low. Next is for concentration of the for concentrating the different materials in the food industry, as well as in the food industry, as well as in the other biotechnological industry. So basically the reverse osmosis process is used in food industry for concentration of the milk, for concentration of the juices, coffee, as well as for de-alcoholization of the wines and beer. So for making the constant concentrations of alcohol in the wine and beer, for that purpose also we can use the reverse osmosis. Reverse osmosis also primarily used for the wastewater treatment. So basically for treatment of the wastewater producing from the textile industry, pulp and paper industry. So this type of wastewater contain a lot of the organic material as well as the salts. And in the metal industry, where a lot of heavy metals comes from in the wastewater, so this type of wastewater can be treated by using the membrane based reverse osmosis processes. Now membrane materials used in the reverse osmosis. So there are basically two different types of membranes are used in the reverse osmosis, commercially available reverse osmosis. First is the cellulosic membranes, where the cellulose acetate or cellulose triacetate are used. So this type of membrane I have already explained in the introduction of the membrane technology, that this type of membranes has the very narrow range of the pH, as well as the narrow range of the pH, and don't have the high fluxes, but this type of membranes have the high resistance for the chlorine. Okay, and second type of membranes are the polyamide membranes. So these materials, sulfones, polyvinyl alcohols, are also used, but mainly the polyamides are used in the reverse osmosis membranes. So nowadays whatever membranes we are using our homes, that are the polyamide membranes. So that polyamide membrane has the base of the polysulfones, which will provide the high strength to the mechanical strength to the polyamide membrane, as well as that, and that both membranes are casted on a polyester, non-fabric polyester texture. So that is the reverse osmosis membranes which we are using in our homes has the three layers membranes, composite membranes. First is the polyester texture, which has the very high porosity and large pore size, with the large pore size. Above that we have a very thin layer of polysulfone membrane, polysulfone ultrafiltration membrane, which has the micro size of pores and provide the high strength to the material. Then there is a very thin layer of polyamide. That polyamide will provide the separation, that will remove the water that will allow to transfer the water molecules from the mixture. Okay, so the separation occurs due to polyamide only, and other material will provide the mechanical strength to the polyamide layer. Okay, so generally the membrane used nowadays are the polyamide membranes. So that will give you the high fluxes and can be used for wide range of pH, but the problem is lower membrane life as well as the less resistance to the chlorine. Okay, so these are the, for that we are preheating the water in our home appliances. So in our home appliances we have a mechanical separator also, where the small micro filtered separator also, where we can remove the particles of the solid small solid particles. Then we have the carbon cartridge, which can use to separate out the chlorine and other dissolved gases in the water. So that pre-treated water then sent to the polyamide reverse osmosis membrane. There it will be purified. So these two type of membranes are used in the reverse osmosis. Now the osmotic pressure. So this is very important concept in the reverse osmosis. So basically in reverse osmosis we are reversing the osmosis process. So in osmosis process, what is the osmosis process? So in osmosis process, if you are separate out the two different concentration of the two different solution which has the two different concentration by using a semi permeable membrane, then water will flows from the dilute side to the concentrated side. So in reverse osmosis, the just opposite happened. The water will flow from the concentrated side to the diluted side. So how it will happen? Because we will provide the mechanical pressure at the concentrated side, so that will overcome the osmotic pressure. So you have to calculate the value of osmotic pressure. So here pi represent the osmotic pressure, pi equal to vi ci rt. So this is the Van 't Hoff equation which is used to, this is the Van 't Hoff equation which is used to calculate the osmotic pressure. So osmotic pressure difference across the membrane can be calculated by pi dash minus pi double dash. This is the permeate side osmotic pressure, this is the feed side osmotic pressure. So the difference will be equal to the total osmotic pressure difference across the membrane. So you have to give the more mechanical energy or more mechanical pressure towards the feed side than the delta pi, then it will be reverse osmosis. Okay, so it can be calculated like VIRT ci minus ci dash minus ci double dash. This is the ci is the concentration of salt in the feed side, ci dash is the concentration of salt in the feed side, ci double dash is the concentration of salt in the permeate side. Vi is the Van 't Hoff factor, which is equivalent to the numbers of ions present in the molecule of salt. So if it is an NaCl salt, the Vi value is 2. If it is a BaCl2 salt, Vi value is 3. So in this way you can calculate the value of Vi. Now there is a small derivation to calculate how much minimum energy required to separate the salt from the water. So suppose you have a salt water mixture and you want to separate out the salt and water from it. So what is the amount of energy required? So this derivation is based on the thermodynamics, the first and second law of thermodynamics, and the basic concept of the reversible thermodynamics. So then we can calculate the, from this derivation we can calculate the what is the requirement of energy to separate out the salt and water from their mixture. Okay, so we will start with the second law of thermodynamics, that is the ds is greater than equal to dq by t. So this equation, this expression represent the, basically this expression represent the definition of entropy. Here S is entropy. The change in entropy should be greater than if the process is irreversible and equal to if process is reversible. dq is the change of heat of the system and T is the absolute temperature of the system. So ds is greater than equal to dq by T. This is the second law of thermodynamics. And from the first law of thermodynamics, for a closed system we can know that du is equal to dq plus minus dw. U is the internal energy of the system. So change in internal energy of the system of a closed system, this is defined for the closed system, should be equal to dq change of heat plus minus dw. dw is the work done. So if work done on the system, then it will be positive. If work done by the system or work done, then it will be negative. Okay, now for the, this is the first law of thermodynamics. So we can combine both laws and calculate the how much energy required in this process. Okay, minimum energy requirement in this process. So this dw is work done on the system, can be represented by dw equal to pdv minus dw dash. So pdv is the reversible work, pressure multiplied by change in volume. This is the reversible work done on the system. minus dw. This is the extra work, irreversible part of the work which is required, because any actual process, any practical process is a irreversible process, and this pdv is only the reversible work. So minus dw represent the extra irreversible works required in the system. Okay, so if you rearrange this equation, you can write dq equal to du plus pdv minus dw. Okay, so just we substitute the value of dw here, then we rearrange this equation. It will become dq equal to du plus pdv minus dw. Now just substitute the value of dq from this equation, equation number 1. So it will become dq equal to tds. So tds should be greater than equal to du plus pdv minus dw. So this is the equation number 3. Now this is the same equation. If you change the sign, this is the same equation. If you rearrange this equation, you can put dq, du and pdv in the left hand side of the equation. Then it will become tds minus du minus pdv should be greater than equal to minus dw. Okay, now from the definition of Gibbs free energy, G is the Gibbs free energy. Gibbs free energy is defined as H minus Ts. H is the enthalpy of the system, T is the absolute temperature, S is the entropy of the system, and H enthalpy can be defined as U plus PV. So this is the definition of enthalpy. Enthalpy equal to U plus PV. U is the internal energy of the system, P is the pressure of the system, V is the volume of the system, minus T, T is the temperature of the system, S is the entropy of the system. So this is the G, Gibbs free energy equal to U plus PV minus Ts. Now if you calculate change of Gibbs free energy at constant temperature and pressure, so that will be equal to G dGe, delta G del dG at constant temperature and pressure should be equal to du plus pdv. Why? Because P is constant here, so P dV minus TdS, because T is constant here. Okay, so if you compare equation 4 and 5, then you can replace the value of du plus pdv minus ds from the in this equation, in fourth equation. So it will become minus dg at constant temperature and pressure should be greater than equal to minus dw dash, and this is the irreversible work. This is the actual work required for the system. Okay, if you integrate the both side, it will become g1 minus g2 should be greater than and equal to then minus dw. So this is the work required for the system, and when you change the sign, then it will become g1 minus g2 should be less than equal to dw. So this is the minimum work required for the system for doing this, for changing the system, for for providing the change in the system. Okay, so this is the work required for the separating the salt and water from the mixture. Okay, so this is the minimum work required. So minimum work required for separating the salt and water from their mixture should be equal to change in Gibbs free energy in the both for step 1 to step 2. So in step 1 both are in the mixture form, and in step 2 both are in the separated form. So this is the changes Gibbs energy in both steps. So that will be equal to the minimum work required. So this is the calculation based on the thermodynamics, how much work required for the separating out the salt and water from their mixture. So this is actually the theoretical work. It is the minimum work, and the actual work will be higher than this work based on the efficiency of the pump you are using or efficiency of the other equipment you are using. There are pressure drop in the pipes, and there are pressure drop in the flow channels. So that work will be added in this work. This is the minimum theoretical work required for separation. Now the transport model of the reverse osmosis. So I have already explained you that reverse osmosis works on the solution diffusion mechanism. So in the solution diffusion mechanism, the species present in the liquid selectively absorb on the surface of the membrane, then on the membrane, then diffuse across the membrane due to the concentration difference, then dissolve at the other side of the membrane due to the and separated out. Okay, so while there is a permeability, or the membrane have special selectivity towards the water than the higher selectivity towards the water than the salt. So it is absorbed, selectively absorbed, water molecules are selectively absorbed on the surface, then that will be selectively diffuse across the surface, then dissolve at other side of the surface. Okay, and the separation occur due to the different values of absorption coefficient and diffusion coefficient of water and salt in the membrane material. So there one more method, one more physical concept applied here, that is the concentration polarization. So concentration polarization is defined, can be calculated by film theory model. So basically I am explaining here that what is the concentration polarization. So because membrane is selectively transporting a, a specific species present in the mixture. Suppose you are separating water and salt, so membranes are is selectively transporting only the water from the mixture. So what will happen, the concentration of salt is start to accumulate on the surface of the membrane, because it's the solid body, so it is in the stationary condition, so you have a lower velocity of the solution here. So the concentration of salt will be higher at the surface of membrane. It will not accumulate it or precipitate on the surface. If it will precipitate, it will be the membrane fouling, but it will start to, concentration will be higher. So if the concentration of the bulk solution is C21, then the concentration of salt at the surface will be C22, where C22 is higher than the C21. So this phenomena is called the concentration polarization. So you can calculate the concentration polarization by using the film theory. So I have already explained you the film theory model. This is the mathematical model, and I have already asked you the question about the this derivation in the mid semester exam, so I am not repeating this. So this is the final equation. So C22 by C21, so this is the concentration at the surface of the membrane, this is the concentration in the bulk. So C22 should be higher than C21. That should be equal to, nearly equal to, exponential of JB by K. So JB is the total water flux in the meter cube per area per unit time. So volume per area per unit time. So this is the water flux, total water flux, divided by K. K is the mass transfer coefficient of the membrane of the film, that water film which contains the higher concentration of salt. So that is the based on the film theory. Okay, here K is the function of flow rate of the feed flow rate in the feed channel. Okay, so if you have the higher concentration of C22, you will get the lesser flux. If the fluxes are higher, then you have the higher concentration. If the fluxes are lower, you have the lower concentration polarization. Okay, so this equation you can use to calculate the concentration polarization, or the concentration of salt at the surface of the membrane. Okay, now the solution diffusion model. This is all about the, in this equation you are relating the rejection to the concentration polarization. So R observed means the observed rejection of salt, which is defined by this formula. Rejection is C22 minus C23 by C22. Here C22 is the concentration of salt at the surface of the membrane in feed side. C23 is the concentration of salt at the surface of membrane at permeate side. So the both side of the membrane. So C22 minus C23 means how much salt concentration changes from the feed side to the permeate side, divided by C22, it will become the rejection. So this is the actual rejection which happens across the membrane, because C22 is the concentration at the surface. But what you observe, because you cannot calculate the experimentally measure the concentration at the surface, you can only measure the concentration at the bulk. So that will be equal to C21 minus C23 by C21. So this is C21 is the concentration of salt in the bulk solution, C23 is the concentration of salt at the other side of the membrane at the permeate side. So C21 minus C23 by C21 is the observed rejection. So you can correlate the observed rejection and actual rejection based on this formula. Okay, so this is the simple derivation, you can follow this. I have already asked this derivation during the mid semester exam. So the final result is ln 1 minus R observed by R observed equal to ln 1 minus R by R plus JV by K. So this is the formula which correlate the observed rejection to the actual rejection and the JV by K, concentration polarization. Okay, so you can use this formula to calculate the actual rejection when you know the observed reaction experimentally. Now there are some mathematical model which calculate the mass transfer across the, which can be used to measure the fluxes across the membrane. That is the solution diffusion model that I have already explained you. Okay, so final equations are in the solution diffusion model. This is the derivation. Again, this derivation I have explained during in before mid semester and asked in the mid semester exam. So I am not repeating this derivation again. I am just going to the final expression. So this is the final expression. So N1 is the flux of water, that is equal to A is the hydraulic permeability multiplied by delta P. Delta P is the pressure difference across the membrane minus delta pi. Delta pi is the osmotic pressure difference across the membrane, which can be calculated by Wand's equation. So J1 equal to A multiplied by delta P minus delta pi, and N2 N1 is the flux of water, and N2 is the flux of salt. So N2 equal to B multiplied by delta C. Delta C again is the concentration difference across the membrane, means C22 minus C23. Okay, and B is the solute permeability. So these two equation can be used to calculate the water flux as well as the solute flux or salt flux across the membrane. Okay, here pi can be written is the function of C22 minus C23 delta pi. So delta pi can be written as B multiplied by C22 minus C23, where B equal to RT multiplied by V. Okay, or if you are separating the NaCl salt, then B equal to 2RT. So 2RT multiplied by C22 minus C23, that will be equal to delta pi. Now if you are using the pure water, now how to calculate the value of hydraulic permeability A and the solute permeability B, because these are important. Once you know the hydraulic permeability of membrane and the solute permeability of the membrane, you can easily calculate the values of flux at any given concentration or any given pressure. Okay, because these are the process variables. You know the concentration of the water, and water is the desired concentration which you want at the permeate site. Then you can easily calculate the fluxes. What are the fluxes you will get? Okay, so for calculating the value of N1 and N2, you can design the specific experiment. For calculating the value of A and B, you can design the specific experiments. So in this experiment, first you do the experiment on the membrane using the pure water. So what's happened in the pure water, the concentration of salt will be 0, so delta pi will be 0. So you will get N1 equal to A minus A multiplied by delta P. Okay, so N1 is the flux of water. So you take a membrane, put in the system, and do the experiment at different pressure, different pressure difference using the pure water. Okay, so and measure the amount of water you are collecting at the permeate site, which is the flux. So we have done the experiments, like the one pressure drop is like 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. So when you plot N1 by delta P by using this equation, you will get a straight line. So here from this equation you can say that A equal to N1 divided by delta P. Okay, or delta N1 divided by delta P. So if you know the value of N1, you know the value of delta P, you just plot the value on the graph and make a straight line, and the slope of the straight line will represent the value of hydraulic permeability. So in this way you can calculate the value of hydraulic permeability. Okay, now the second thing is measurement of the value of B. But B cannot be measured directly. Why? Because the concentration of salt at the surface cannot be measured. We have already explained you that there is a concentration polarization on the surface. So you cannot measure the concentration of the salt at the surface of the membrane directly. Okay. So for that we will combine this equation to the next equation, which is this equation which we have derived for the concentration polarization. So we have already explained that this equation R observed is the observed rejection, R is the true rejection. So in here R can be written by this formula, and if you rearrange this formula, then R will be equal to 1 minus B. B is the solute permeability, C22 minus C23 divided by JV. JV is the total flux divided by C22. Okay, and again if you use this formula, replace R by this formula and solve this. This is not important for you. Just you have to follow the steps, and you have to only remember the final value or the final expression. So the final expression equal to ln 1 minus R observed divided by R observed JV equal to JV by K plus ln B. Okay, so this is the final equation. So in this equation, R observed is the rejection of salt. So rejection of salt can be calculated like in feed system you have the 500 ppm salt. At the product you will get the 50 ppm salt. So 500 minus 50 divided by 500. This is the rejection of salt. Okay, so in this way you can calculate the R observed. JV is the total flux. So how much water you will get in the permeate side. Suppose you are doing the experiment, you will get the 100 ml water in 10 seconds. Okay, and the area of the membrane is 0.1 meter square. So 100 divided by 10 10 multiplied by divide by 0.1. So it will become your amount of flux JV. Okay, so you just substitute the value of R observed there, JV here in this equation, and the plot JV versus this value. Okay, so when you plot this value, how you will get the different values? Of course, by doing the different experiment at different pressure. Once you change the pressure, the value of JV will change, value of R observed will change. You will get a different values. So you can plot just JV versus just this value. You will get a straight line. The intersect of the straight line in y-axis will represent the ln B. So from this value you can calculate the value of B, and the slope will be equal to 1 by K. So by slope you can calculate the mass transfer coefficient K values. So in this way you can calculate the value of K as well as value of B. So this experiment, this design of experiments are first proposed by Kiruma Saurirajan, and it is called the Kiruma Saurirajan model. Okay, so mass transfer coefficients are also calculated by the, because generally the mass transfer coefficients in the boundary layer theories, mass transfer coefficients are the function of flow rate. So when you change the flow rate, the value of mass transfer coefficient will change. Generally the mass transfer coefficient K are related to the flow rate by this formula, K equal to A Q to the power B, where A and B are the constant. So just you conduct the experiment at different flow rates and plot the, and then calculate the value of K by using this formula, at different flow rates, and just plot these values in this equation and plot ln K versus ln Q versus ln K. You will get a straight line. The intercept of a straight line will represent the value of A, and the slope will represent the value of B. So generally for turbulent flow, value of B is 0.8, and for laminar flow, value of B is 0.33. Value of A generally depend upon geometry of the spacer. Or if you are change the geometry of the spacer, value of A will change. Okay, so this is all about the reverse osmosis. This topic contains a lot of derivation, but you need not to go for the derivation. You have to remember these formulas, because direct numerical based on this formula may be asked in the exams. So you should remember how to calculate the value of A, how to calculate the value of B from the formulas.